Okay, so in this part, we're going to talk about how to evaluate classifiers and some of the subtleties involved in evaluating classifiers. So we just talked about the discriminant analysis and generative classifiers. Now I'd like to spend a little bit of time talking about some of the details of evaluating the performance of our classifiers. Okay, so I'm going to load in the bank data, which has about 4,500 entries, and there's missingness in this data, so we're going to have to deal with that, and I'm not going to do that in a very sophisticated way. We have an outcome which is, I think it has to do with defaults of credit lines. Okay, so I'm going to start by doing a training test split, and if we look at our training data, then we can, for example, look at the two different classes and the densities of those two different classes with respect to certain covariates. So, for example, the age covariate, the density seems to be a little less sharply concentrated for the no outcome as opposed to the yes outcome. You have, I think these are defaults at young ages and at very old ages. Okay, so I have a lot of code that's hidden from you here, but this is just more sophisticated pre-processing scripts. It splits the data and then also performs some scaling operations and some basic imputation. But you'll have to trust me that I'm doing valid test set. All of my test operations, creation of the test set, are based off of parameters that are trained from the training set. So I'm doing everything legally in terms of my training test split. So evaluating a classifier. So most classifiers are soft in the sense that they actually can output a score. They can be turned into a continuous score where smaller means that you're going to more readily predict as a 0, and larger you're going to be more readily predict as a 1. And there's extensions of this to multi-class classification. This isn't just restricted to binary classification, but for these purposes, we're going to talk about binary classifiers. And so the logistic regression we'll see can output a probability. Support vector machines has this distance from the margin in a certain direction. That's also a score, so that can be turned into a soft classifier. K-nearest neighbors, you can report the percentage of neighbors that had the certain class, like the ones. And LDA and QDA, we actually had these scores, which in LDA was a linear score, and then we thresholded it, but we don't have to threshold it. We could just output that score. QDA, similarly, we can output that quadratic score that we had. Naive Bayes, we have also the log likelihood. All of the likelihood ratio. All of these really are likelihood ratios in the end because they're generative methods, and we're using the Bayes plug-in rule for the Bayes classifier. And so all of them are estimated likelihood ratios, and all of those can be thought of as just scores. Now, the reason why we like this is then we can move that threshold. So in the example of the likelihood ratio, we could change that tau threshold and then make it so that we predict more ones or less ones, depending on where we set that threshold. And this is important because we're going to talk about unbalanced classification problems where you have a lot more ones than zeros, and maybe you'd like to tune this threshold in a very specific way based on your application. So we'll talk about that in a little bit. Okay, so that's about soft classification. Now, if I gave you a certain threshold and then I predicted some points to be ones and some points to be zeros, and then we actually saw what the test set was, what the test y's were, then we have true ones and true zeros. And so we can compare these two and form what's known as the confusion matrix. So those which are we predicted as ones and actually turned out to be ones, we call those true positives. So predicting as a 1, we say that's a positive. But if we were wrong, it's a false positive. Predicting as a 0 is, and then we were wrong, so it actually was a 1, is a false negative. And then a true negative is if we predicted as a 0 and we're correct. Okay, so false positive rate is the number of false positives divided by the total number of true positives, right? So this is the false positives, false positives divided by the number of false positives plus the true negatives. True negatives. So false positive rate is the number of false positives divided by the number of true negatives, which is this false positive plus true negatives. So this is number of ones that were actually turned out to be zeros divided by the number of zeros. So this is sort of like, if you're focusing on the true zeros, how many of those did you actually say were ones? What ratio of those did you actually say were ones? That's what false positive rate is. True positive rate is sort of the opposite. If you focus on the ones, that's the true positives divided by true positives plus the false negatives. That's what's in the denominator here. How many of those actually turned out to be positive, predicted positive? So this is sort of a ratio of the ones that you got right, right? So you want the false positive rate to be small. You want the true positive rate to be large. We also call this the recall. And the interpretation there is that there are some ones out there, right? There are some ones out there. How many of those did you recall? How many of those did you actually find? And this comes from the history of calling it precision and recall comes from the information retrieval world, where you imagine there's many documents and you're trying to return some important or relevant documents. Okay. Precision is typically paired with recall, and it's the number of true positives divided by the number of true positives plus false positives. That's the number that you predicted as a 1. So look at precision and recall. This true negative never appears. True negatives never appear here, right? It's only it's this true positive divided by something, and that something is either the predicted ones or the true ones. That's what the recall and precision are. Whereas the false positive rate and true positive rate, which are typically paired together, are looking at different columns of the truths. So one is the false positive rate plus true negative rate, that's the true zeros, and the other is the true positive rate divided by the false negative rate, that's the true ones. And so the false positive rate and the true positive rate are sort of measures of how well you're predicting the ones and the zeros, and it's sort of even. If you flip-flop these, you could get the roll of 1 and 0, you could get the original false positive rate and true positive rate from the new false positive rate and true positive rate by doing appropriate subtraction from 1, by doing appropriate transformations. So the way you should think about this, false positive rate and true positive rate, they sort of are agnostic in some sense to what is labeled 1 and what is labeled 0. There's nothing special about 1s and nothing special about 0s except for the fact that this is false positive rate and this is true positive rate. But you could just sort of switch the roles and then you could get one from the other. Whereas precision and recall are not agnostic. One is very special when you're looking at precision and recall. And you can imagine retrieving documents. If you retrieve 20 documents out of 100,000, then your predicted ones is there's only 20 of them, right? You could think of those as the ones. There's only 20 of them for in the information retrieval case. And your precision is how many of those documents were actually relevant. That's very important in the information retrieval setting. And the recall is how many of the ones that are just out there in the world, in the wild, did you actually get back? So maybe you're in an application where you really care about your precision. Maybe you're going to return 20 documents and you just hope that there's a lot of relevant ones in there, but you don't care too much about your recall. Maybe there's 1,000 relevant documents, but you don't care too much about how many you recall, right? But in that case, 1 is a very special thing. There's perhaps only some relevant documents, and the irrelevant documents are not as special in some sense. So I'd like to draw that distinction, and it really makes a difference when we look at how we evaluate our classifiers. Okay, so we'll return to that in a second. So suppose I'm going to create a score. I'm going to make a score that's just this second column of XTE. And I'm going to say that if that second column has a high value, then I'm going to predict as a 1. If it's a low value, I'm going to predict as a 0. And this isn't a coincidence. I chose this because I looked at this plot of this is the red is no and the blue is yes. I looked at this and said, well, this duration parameter, if it's large, you tend to have a yes response variable, have a positive response. So if we look at this and we look at the confusion matrix, this is our confusion matrix for this score. If we threshold at 1, so this score isn't enough. We have to choose a threshold, and I have. So this is before the standardization, but I've standardized this. So 1 is going to be somewhere around here. So it's going to do a fairly good job of separating out the yeses from the nos. It's going to do something at least. And if you look at the true ones that were predicted 1, you get 73 of them. The true zeros which were predicted 1, you get 108. So immediately we see that of the predicted ones, there's more zeros than ones. So you're not doing that great on precision. But of the predicted zeros, you have a lot more zeros than ones, right? And so you're doing a good job of predicting the zeros, and it's because there's a lot more zeros than ones. And we didn't see that from this plot. We didn't see the relative proportion of yeses and nos for the response variable, but it actually really mattered because it turns out this is very imbalanced. This is an imbalanced data set. There's a lot more true zeros than there are true ones. So this is going to really matter. And as we change this threshold, this 1 threshold, let's move it to 2. Now we're being a bit more hard-nosed about what we call a predicted 1. So our predicted 1s overall are going to decrease. And what you tend to see if you're not doing random guessing, that your true ones, your precision, is going to get better here. So the true ones as a proportion of all the predicted ones is going to get better, right? And that's going to be our precision. And so there's a shift from true zeros. So now the true ones that are predicted ones, there's more of them than the true zeros. But of course, the number that we're returning, the number of predicted ones, is getting smaller, right? And so we're being a little less hard-nosed about the zeros. But if you think that ones are special, maybe this is the decision you would make. Maybe you would increase this threshold by a bit. Okay. Now we can do something a bit more extreme than, it was a bit ad hoc choosing that duration as a score. So let's do something else. Let's just say we're going to look at all of our nearest neighbors. So we're going to use a KNN classifier, and we haven't talked about this in the classification context, but you can envision what's going to happen. And I'm going to actually build this thing by hand. So what we're going to do is we're going to say for every point in our training set, we're going to say, well, let's use it to predict our test set. So for every point in the test set, you say, what are the 10 nearest neighbors in the training set of each of those points in some Euclidean metric? So if we look at those nearest neighbors, for example, for the first sample in the test set, we have index 1047, we have index 967, and so on. All of these are the indices of the neighbors in the training set. Then let's just look at the y's for those indices, and then take their mean. Turns out it's 0. They're all 0, right? And the actual test y was 0. So we did a good job here. We predicted it correct. This would count towards the zeros, toward that last column in the confusion matrix, which is the true zeros and predicted zeros, right? And so you can imagine doing this method more generally. This is how K-neighbors classifiers work, is that you find the, say, 10, if number of neighbors is 10, 10 nearest neighbors in your training set for each test point, and then you just average, right? And you see, does that exceed or not exceed some value, right? And so we're going to think of this average as our score, right? Okay, so we can do the same thing, and then we can set our threshold to be 0.2, for example. That's saying that if 20% of your neighbors are 1s, then we're going to say predict as a 1. In that case, we're not being very, very hard-nosed about the predicted 1s, and we're going to get a poor precision. But if we increase this, well, we're not increasing it there. Okay. Yeah. If we look at the score duration, another way to think about this, so let's think about the precision and recall now. If we think about just how many of the top, how many are we going to return? If we think about it in the sort of the information retrieval context, what we're doing is we're going to order all of our training points by their score, or all our test points by their score. And then let's just look at what the Y's are for those test points. So if we order them, this print top K is just ordering them and printing the top 10, for example. If we look at this duration score, so this is just the duration, a standardized version of the duration variable. If we look at this, the highest duration is around 10, is over 10. Right? Its test point turns out to be 0. So the highest duration one actually has a response of 0, and we would have predicted it as a 1. Right? But ordering these, we do have a pretty high proportion of 1s in this top 10. Right? We have 1, 2, 3, 4, 5, 6. So 6 out of 10 isn't too bad. That's 60%. Right? And if you consider how many zeros are in this data set, this is actually quite good because the number of zeros in the data set is on the order of, I think it's a factor of like 10 to 1. Right? If we look at this, no, not 10 to 1, but it's maybe 3 times the number of zeros to 1. Or no, it is around 10 to 1, maybe 8 to 1. And so you can imagine that if we just did random guessing, instead of ordering by score, if we did random guessing, we would have only like 20% or less than 20% of these would be 1s on average. And so this is actually a lot better than random, even though 60% doesn't seem like that good on the face of it. Right? So let's look back at this. The number that we were talking about there is the precision. It's the number of 1s here that the percentage of these that are 1s, of these top K that are 1s. And we can think about the threshold that gave us this top K. We thresholded it right below 4.602. So maybe we chose a threshold of 4.6, and these are the ones with the scores above 4.6. Right? That's a high threshold. Right? And so the precision was pretty good there. That was around 60. It was 60%. The recall is going to be pretty small in that case, right? We only returned the top 10, and the recall, if you look at it, is the proportion of actual ones that you returned, right? The true positives plus false negatives. It's the proportion of actual ones that you returned, and that's certainly not going to be that high if you only return 10 of them. Right? If there's on the order of over 100 actual ones, then your recall is going to be less than 10% if you return the top 10. Right? So there's going to be this trade-off naturally between precision and recall. As you increase the number, this K, the number that you return, and predict as a 1, the recall is going to start to increase, but your precision probably is going to start to decrease. If your classifier is doing something if your score is doing something reasonable. So if we plot the true positive rate against the false positive rate, that's what we call the ROC, receiver operator characteristic curve. So this ROC curve, it starts at 0, 0, and then as you increase it, it will give you a curve like this. Random guessing is just a straight line from 0, 0 to 1, 1. And the way this curve was derived is we are just going to change the threshold that I said before. And each time we change the threshold, we get a different confusion matrix, and we can recalculate false positive rate and true positive rate. And that's going to give us a point here. Right? So we keep changing this threshold, and it keeps giving us a new point. And we're going to get a curve like this. And if we're going to do a better job, we're going to have a higher true positive rate for a lower false positive rate, and we're going to be up in this corner. Up in this corner is better. And typically, for very easy classification problems or good classifiers, we see a curve that goes up and juts over like this, the ROC curve. Right? And I talked about changing this threshold. Equivalently, you could think about changing this k in the top k that you return, because we already said that choosing this k equals to 10 is equivalent to choosing a threshold of 4.6 or so, right? And you can just imagine returning the top, instead of 10, 20, and that will give you a different point on this curve, because it gives you a different confusion matrix and hence a different TPR and FPR. So we can plot this for that duration score. We can also use a different score, say the k nearest neighbors score that I mentioned before, and we can compare these two. Turns out the duration score always dominates the KNN score. The KNN is not doing that well. And remember, more in this top left-hand corner is better, because a higher true positive rate is better for a given false positive rate. Okay, another thing that we can look at is this precision against recall. I mentioned precision is paired with recall typically. And in that top 10, we had a high precision. It was around 60%. So it's one of these points here, up here is that top 10. Right? The recall I mentioned was very low, is around 10%. So it's probably a point like this, is the top 10. Typically with precision and recall, as you increase that k, you're decreasing the recall, and you're increasing the recall and decreasing your precision. And then random guessing is going to be the proportion of ones in your data set, right? So you're comparing against a line that's down here somewhere. So we're doing a lot better than random guessing, right? Random guessing for the ROC curve is going to be a line which just goes linearly up like this. So we're doing better than random guessing by quite a bit in both of these curves, even though as a precision, 60% doesn't seem that great. Generally, when it comes to unbalanced data sets, we prefer the PR curve, and this data set is very unbalanced. And that's because we didn't really see anything significant from the ROC curve that had to do with this data set being unbalanced. But typically with unbalanced problems, we're going to tune our threshold so that we are a little more hard-nosed about precision, right? So like perhaps you have an application where you want to predict a subset of the individuals who are very likely to default. In which case, and you don't really mind if you get all of these individuals, you just want to get those which are very likely to default and deal with them separately. So maybe then you would care more about precision than recall. Whereas ROC, in the ROC curve, it's not clear how to make this interpretation. Another way to think about it is you care more, another type of application is you care more about recall than precision. There are applications where this happens as well, like you want to get all of an instance, and then you just hope that your precision is as high as possible. Okay, so I'd like to make a comment that good ROC curves should be in the top left corner, just like we said before. That good PR curves should be large for all recall values, so just dominating above. Higher precision is better. PR is better for large class imbalance, for problems like this where there's large class imbalance. And that's because with large class imbalance, we typically don't think that it's great that you did a good job of predicting zeros, because a lot of times then you can do very well just by only predicting zero. So that's something to be aware of. And like I said before, ROC sort of treats the zeros and the ones equally in some sense. Each type of error is given its equal weight. Okay, so this leads to an exercise. We're going to apply LDA and QDA to the same data set and then compare the PR curves. So just like we did with the duration score and the nearest neighbor score, also do this for LDA and QDA. So I'm going to answer this question. Just pause the video and work it out yourself. Just don't look at the rest of the notebook. Yeah. Okay, so let's jump back in. The way I do this, it's pretty straightforward. I'm going to create these predicted scores list of these predicted scores for the test set. I'm going to start with that duration and nearest neighbors and create a list of tuples of these scores. It'll be clear why I organized it in this way when I go to plot the PR curves. So we'll fit LDA, and LDA, it's very easy. There are no tuning parameters unless you want to make constraints on LDA, but I'm not making any constraints. So I just initialize it in scikit-learn, and then I fit it on the training data, and then I predict, but I'm going to use log proba with LDA, and that's because this is going to output a score, the log probability, and not just the prediction, which would be a 0 or 1, which isn't helpful for me because I want to plot the PR curve. And then this 1 is the probability of being a 1 and not a 0. And so I'll output these scores and then save them. And then I do the same thing with QDA. It's very simple. Okay, now that we have it, I'm just going to plot these PR curves, and then the metrics method, or the metrics module within scikit-learn also has precision recall curve. It makes this pretty easy, where it takes in the test-wise and then and the scores as well. And I'm just going to do this for all of the models that I've trained and plot precision against recall. And when we do this, we actually get that duration does about pretty much the best. I wouldn't really interpret too much here. Nearest neighbors is the only thing that does particularly poorly. And LDA and QDA seem to just be finding that duration is a good predictor in some sense. Probably the beta has a high weight on the duration, whereas nearest neighbors is not going to select which variables are more important in some sense. It just uses the Euclidean distance. So, so that's what we find. There's not really that much advantage to using anything other than duration in this case.